Public Exam Review for Advanced Math 3200, Unit 3, Chapter 2 on Radical Functions. In this presentation, we will look at solving radical equations by graphing. Here we will focus on relating the roots of radical equations and the x-intercepts of the graphs of radical functions. We will also determine approximate solutions of radical equations graphically. In the first example, we are asked to solve the square root of x plus 6 equals 2 by graphing. When you solve an equation, you should ultimately end up with x equal to something. In order to solve this equation, we will use two methods. In the first method, we will graph the left-hand side of the equation, y equals the square root of x, and the right side of the equation, y equals 2. We will graph this as a system of equations, and the solution will be the point of intersection of the two graphs. Notice that the graphs are drawn here on the coordinate plane, and the point of intersection occurs when x is equal to a -2. In sketching the graph of this function, we have y equals the square root of x plus 6. That's the same as y equals the square root of x minus a -6. Notice that we have a horizontal translation equal to a -6 units to the left of the base graph of y equals the square root of x. The other graph, y equals 2, will be a horizontal line that passes through y equals 2 for all values of x. The solution to this system of equations is this point of intersection, and the corresponding value of x gives us the solution to the equation. So the solution in this case would be when x is equal to a -2. We can check our solution by substituting this value of x back into the original equation. A -2 plus 6 is equal to 4, and the square root of 4 is equal to 2. So we know that our solution must be correct. Another method can also be used to solve this equation by taking all terms and putting it to one side of the equation. So we have the square root of x plus 6 minus 2 is equal to 0. Again, we can graph this as a system of equations where we have y equals the square root of x plus 6 minus 2 and the value of the line y equals 0 as a system of equations. Y equals 0 will provide us with the x-intercepts of the graph. And notice that the x-intercept here also occurs at x equals a -2. In sketching the graph of this function, again you can use your knowledge of transformations to do so. If you have y equals the square root of x plus 6 minus 2, that can be rewritten as y equals the square root of x minus a -6 minus 2. The -6 here represents a horizontal translation of the base graph of y equals the root of x 6 units to the left. The -2 here represents a vertical translation equal to -2, and the base graph of y equals the root of x is moved downward 2 units. Again, the x-intercept of this graph will provide us with the solution to the equation that we were asked to solve. So once again, the solution here is x equals a -2. Similarly, we have to solve the square root of x squared minus 9 equals 4 by graphing. The graphs are already provided for you, whereby we graphed both sides of the equation. As a system of equations, we have y equals the square root of x squared minus 9, and the other graph will be that of y equals 4. The square root of x squared minus 9 is illustrated here in this graph for values of x that are greater than or equal to 3, less than or equal to a -3, and y equals 4 is the horizontal line. Again, the points of intersection of these two graphs will provide us with the values of x that will solve this equation. So in one case, we have x equals a -5 as one solution, and in the other case, we have x equals a +5 as the other solution. Substituting these values into the original equation, we can check to see if these answers are correct. When x equals a -5, we have -5 squared, which is 25, minus 9 is 16, and the square root of 16 is equal to 4. When x equals 5, 5 squared is 25, minus 9 is 16, and the square root of 16 equals 4. So we know that these solutions are correct for this equation. In the second method, we can solve the equation by bringing all terms to one side of the equation and making it equal to 0. Therefore, we will graph the function y equals the square root of x squared minus 9 minus 4, and we will look for any x-intercepts of that graph. That is, the values of x that make y equal to 0. And similarly, we come up with the same answers. X equals a -5 and x equals a +5. In sketching the graph of this function, you can use your knowledge of transformations, but it is important to remember that there are restrictions on the domain of the function. When graphing y equals the square root of x squared minus 9, you have to remember that you cannot take the square root of a negative number. So we know that x squared minus 9 has to be greater than or equal to 0. That means x squared has to be greater than or equal to 9. In order for this to happen, x has to be greater than or equal to 3, or x has to be less than or equal to a -3. And that's why you have these endpoints here at -3 and a +3 on your graph. And similarly for the other function as well. The endpoints occur at -3 and a +3. Let's look at some examples. Which graph can be used to solve the square root of x squared minus 9 equals 2? If you notice, in all four possibilities, we have horizontal lines passing through y equals 2. So we will solve this as a system of equations, whereby we look at the solution for y equals x squared, the square root of x squared minus 9, and the line y equals 2. So to graph this function, again, you have to remember that the graph of y equals x squared minus 9 represents a parabola that opens upward. The vertex of that parabola passes through the point 0 and -9. The x-intercepts of this graph will occur at 3 and -3. So we can have the graph of the parabola as follows. We have to remember that the x-intercepts occur for values of y that are equal to 0. So that would be when x squared is equal to 9 and x is equal to plus or minus the square root of 9, where x is equal to plus or minus 3. That's where those x-intercepts came from. However, we are asked to graph y equals the square root of that function. So in looking at the square root of that function, you need to look at your invariant points, which occur when y is equal to 0 and when y is equal to 1. The graph of the square root function will always be greater than the graph of the original function. So the square root function will veer off to the right and to the left for values of x less than or equal to a -3 and x greater than or equal to a +3. As well, we have to look at the line y equals 2, which is a horizontal line that passes through this graph through y is equal to a +2. Again, we are not asked to look for the solution. We are not asked for the solution to this equation. We are just asked for the graph that represents this solution. So the points of intersection here would occur The two graphs will intersect there at this point and again at this point here. So if you notice, the graph that this would correspond with would correspond with C. What you have to look for here are the corresponding x-intercepts of your square root function, which occur at -3 and a +3, and the values of y are equal to 0. So this graph represents the square root of x squared minus 9, and then you have the horizontal line passing through y equals 2. So the correct answer here corresponds with C. In the next example, which graph represents the solution to the equation the square root of x plus b equals x plus c? If we take the left side of that equation, we are looking at y equals the square root of x plus b. In this case here, we are given that the value of b is less than 0. So that if b is less than 0, then that results in the square root of x minus b, which represents a horizontal translation to the right of the base graph of y equals the square root of x. So the base graph of this function, I will just sketch it for you if I could. The base graph of y equals the square root of x looks something like this. And if the value of b is less than 0, then that graph will be moved b units to the right. So that would be the value of b. In the case of the other function, we have y equals x plus c, which represents a linear function. And we are given that the value of c is less than 0. If c is less than 0, that means that that line has a negative y-intercept. So the line would have to pass through the negative y-axis through some value of c, and c is less than 0. So here we would have a straight line that slants upward to the right. And it has to intersect the square root function graph. So this graph resembles a similar situation illustrated in part D. So the first graph here is y equals the square root of x plus b for values of b that are less than 0, and the straight line, the linear function, represents y equals x plus c for values of c that are less than 0. In example 3, we are asked to solve graphically without technology. So here we will graph the left side of the equation and the right side of the equation and try to determine the points of intersection. So we have y equals 2x minus 4 and y equals the square root of x plus 1. Let's provide all the necessary details for each of these graphs. So we have y equals 2x minus 4 represents a linear function in which the slope is equal to 2 and the coordinates of the y-intercept pass through 0 and -4. So we can sketch this graph through 0, -4. A slope of 2 means we go up 2 to the right 1, up 2 to the right 1, and we can connect these points using a straight line. I will adjust the line in a second so that it passes through all 3 of these points. So that represents the graph of y equals 2x minus 4. On the other hand, we have to draw the graph of y equals the square root of x plus 1. That can be rewritten as a transformation of the graph of y equals the square root of x. X plus 1 is the same as x minus a -1, where we have a horizontal translation of the base graph of y equals the square root of x, 1 unit to the left. It is important to note that x plus 1, there are restrictions on the domain of this function. x plus 1 has to be greater than or equal to 0. So x is greater than or equal to a negative 1. So then we have the coordinates of these points. When x is a negative 1, the value of y will be 0. When the value of x is 0, you have the y coordinate to be equal to 1. When you have x is equal to 3, the value of y will equal 2. When x is equal to 8, 8 plus 1 is 9, and the square root of 9 is equal to 3. So this will give us the equation, or the graph of the equation, y equals the square root of x plus 1. You can also use a table of values to sketch the graph of this function if you need to. So we know that the values of x have to be greater than or equal to a negative 1. When x is a negative 1, y will equal 0. When x is 0, y will equal 1. When x is equal to 3, the value of y will equal 2. When x equals 8, the square root of 9 is 3. So in this case here, we look for the point of intersection of the two graphs, which occurs right here for values of x that are equal to 3. So that represents your solution to this equation. X equals 3. Substituting this value for x, we could check our solution. 2 times 3 is 6. 6 minus 4 is 2. X plus 1 gives us 3 plus 1, which is 4, and the square root of 4 is equal to 2. So we know that this must be a solution to this equation. Let's try a more difficult example, whereby we are looking for the solutions of the equation, the square root of 1/2 times x plus 4 all squared minus 2 equals x plus 2. We are asked to provide all the necessary details for each graph. So looking at the left side of this equation, we will graph y equals the square root of 1/2 times x plus 4 all squared minus 2. Before we graph the square root function, we need to sketch a graph of the original parabola. So in looking at y equals 1/2 times x plus 4 all squared minus 2, we have a parabola that opens upward. The vertex of that parabola occurs at -4 and -2. The x-intercepts of that parabola will also be key points on the graph of the square root function. So the x-intercepts can be determined by letting y equal 0. So we have 1/2 times x plus 4 all squared minus 2 is equal to 0. 1/2 times x plus 4 all squared is equal to 2. Multiplying both sides of the equation by 2 helps to get rid of the 1/2, and we're left with x plus 4 all squared is equal to 4. Taking the square root of both sides of the equation results in x plus 4 equals plus or minus the root of 4. Solving for x equals a -4 plus or minus 2. So one x-intercept occurs at -4 minus 2, which is when x is equal to a -6. And the other x-intercept will occur at x equals a -4 plus 2, which is when x is equal to a -2. You could also look for the y-intercept of this parabola. When you have x to be 0, 0 plus 4 is 4, 4 squared is 16, half of 16 is 8, and 8 minus 2 is 6. So the y-intercept of this parabola occurs at 0 and 6. A corresponding point would occur at -8 and 6. So this represents the graph of the parabola, but that does not represent the graph of the square root of that parabola. It's important to keep that in mind. So now, to get the graph of the square root function, we have to locate the invariant points, which occur when y is equal to 0 and again when y is equal to 1. These are the invariant points of the function. As well, so when we're sketching the graph of this function, the graphing method is not always as precise as we need it to be, but we try to sketch it as best we can. So that's the graph of y equals the square root of 1/2 times x plus 4 all squared minus 2. As well, we also need to graph the line y equals x plus 2. That represents a linear function in which the slope is equal to 1 and the coordinates of the y-intercept are at 0 and 2. So to sketch this line, we're at the point 0 and 2. You have a slope of 1, a rise of 1, and a run of 1. A rise of 1 and a run of 1. So this line will pass through the original function. Let me just try to get the graph to connect somehow. I have to adjust this graph in a second so that it passes through all the points of this function. So here we have the points of intersection will provide us with the solution for this equation. So it appears that one point of intersection of this straight line occurs when x is equal to a -2, and another point of intersection occurs when x is equal to 0. They are the values of x that will provide us with a solution to this equation. We need to check our answers here to make sure that they are correct. When x is equal to a -2, -2 plus 4 is 2, 2 squared is 4, half of 4 is 2, 2 minus 2 is 0, and the square root of 0 is 0. A -2 plus 2 is also equal to 0. So we know that x equals a -2 is a correct solution for this equation. Similarly, we have x equals 0. We have 0 plus 4 is 4. 4 squared is 16. 16 times a half is 8. 8 minus 2, we're looking at the square root of 6 on the left-hand side. The square root of 6 does not equal 0 plus 2. So this equation, x equals 0, is not a correct solution for this graph. So your only solution here would be when x is equal to a -2. When using the graphing method, you have to oftentimes estimate where the graphs intersect. And in this case here, it appeared to us that the graphs intersected at the point 0, 2, when in actual fact it did not. So if the graphs were perfectly drawn to scale, this would not be the case. So that's one of the disadvantages of using the graphing method. You oftentimes have to estimate your solutions when using the graphing method. So an algebraic method would be provide us with more precise answers. However, when you use the graphing method, you oftentimes end up with extraneous roots. For the outcomes that are required in this course, you are required to determine the solutions of these equations using the graphing method only. So you can solve radical equations algebraically and graphically. The solutions or roots of a radical equation are equivalent to the x-intercepts of the graph of the corresponding radical function, and you can use either of the following methods to solve radical equations graphically. You could graph the corresponding function and identify the values of the x-intercepts. Or you can graph the system of functions that corresponds to the expression on each side of the equal sign, and then identify the values of x at the points of intersection. That concludes our review of Chapter 2 on radical functions. If you have any questions, please pose them in the question forum, and we will be happy to answer them for you. Thank you, and have a good day.